So we started recording. Yeah, so this lecture today, Monday, January 10th, is a live class session on Probabilistic Programming 3, Regression and Classification. You'll get the chance to ask questions on this particular topic. And then following that, I will discuss the Probabilistic Programming assignment again. And if you have any questions about the assignment, what needs to be done, maybe some of the problem statements or questions need some clarification, then you can ask that now, and I can clarify that for you. I will start with sharing my screen. Yeah. So yeah, as we normally do, I will just give a brief summary of this session, this Probabilistic Programming lecture. Feel free to interrupt me with questions on your microphone or with your microphone, or just to post something in chat, and I'll see it pop up, and then I'll answer them as we go. So maybe just to go back to the schedule first. So Bert explained that the early lectures, they were really important. The probability theory, we've implemented that a bit in this first probabilistic programming session. So it's just about what is a prior, what is a likelihood function, what is a posterior. Then we talked about message passing and these sort of basic workhorse parametric distributions, the Gaussian, the multinomial, the categorical. And we've implemented these in the last probabilistic programming session, where we had a couple of models relatively similar, but with minor tweaks. And I've shown you how you can use probabilistic programming software, specifically Fornilab.jl, as a Julia software package for probabilistic programming, how you might use these to automatically infer posteriors in these models that we talked about. Afterwards, Bert talked about regression, and then there was this extensive theory lecture on both generative and discriminative classification. And then because this B10 latent variable model observational base is it's also quite a heavy, quite a weighty lecture, we decided to move that just before the break, because dynamic models, intelligent agents are also quite weighty and like to more evenly distribute the load. Still, having said that, this probabilistic programming session 3, it just covers regression and classification. It doesn't cover latent variable models observational base yet. In this final probabilistic programming session on the 19th of January, so next week, Wednesday, we will talk about a latent variable model and a dynamic model. But for now, we'll just be talking about regression and classification. The notebook starts with just pointing back to the lecture notes on regression and classification. Again, we're not implementing anything new. We're not discussing new material. We're just repeating some of the material that Bert has explained in an effort to get a better grasp, a better understanding of what this material does or how it behaves. And again, I try to translate some of these problems into very concrete settings, so you get a sort of a feel for, okay, what does my data look like? You can have some prior expectations on what a data set, how it behaves, and whether a regression model, classification model will make sense there. So in this first problem, we're talking about economic growth. It's about the stock market of Turkey. Turkey is, like many countries, one of the countries that went into recession after the US went into recession, so there was a slight lag to it. And the Istanbul Stock Exchange was made public from that period of January 2009 until February 2011. Here I am importing a bit of that stock market data into 536 components. If you plot that over time, that looks like these peaks. And perhaps you've seen a stock market data set before, and you usually see it as these spikes. You have just plotted them as scatter points. But essentially, when we're doing linear regression on this, we're just going to, so the stock market levels are these y components, or these, that's the random variable y, that's the stock market levels, and then the random variable x is just the time at which we're recording. And for this particular problem setting, so stock market data, we have a recording, I think I forgot what I mean, if you're working in a financial firm, you probably have a recording of the stock market data every few nanoseconds, but I think this is one per day or something like that. But at least it's a very regularly behaving input variable. And then this y is subject to some deterministic variation and some random variation. And so we'll be looking back at this this model that you've seen from the theory lectures. There's some function of x that maps into y, and we have some random noise on top of that. And if this noise is zero mean Gaussian distributed, then you can form a likelihood function that's a Gaussian distribution over some function of x, with the sigma squared being the sigma squared of the noise. And if we say that this function is linear, so it's a dot product between coefficient theta and the input variable, then we might also define a prior distribution on this unknown set of parameters theta. If we take this likelihood and multiply it times the prior, that'll be proportional to a posterior distribution over theta. You've all seen this before. That should be fairly straightforward, fairly doable. And as you might expect, the factor graph description of this probabilistic model is equally straightforward. We just have some prior distribution over these weights theta, and we've given them prior parameters, because we, as engineers, you have to provide prior parameters at some stage. You can always build a hierarchical prior, but there'll be some stage at which you have to provide prior parameters. And then in this case, we know the noise variance here to be just 1. And actually, in the probabilistic programming assignment, which we'll get to a bit later, we'll use basically knowledge of this this latent variable model and variational Bayes lecture to simultaneously estimate the weights and the noise variance. But we'll get to that later. So define some input x that'll be filled with data later on, and we have an output y that's Gaussian distributed with this linear function of theta and x, with this sigma squared as the likelihood variance. And I'll give you a very simple factor graph with all of these components plotted. This is just for a single sample, so a single time point, single day. And if you were to treat all of these days as one master data set, and all of these observations are IID, so independent and identically distributed, then you can basically repeat this structure for every observation. And you saw this a bit already in the last probabilistic programming session. Here we had these questions. They were very simple factor graphs with one unknown variable. And let's go down for a bit. And then we added 2 data points, 2 sets of IID observations. So this likelihood is a product over 2 outcomes. So there's x1 and x2 here. You see there's an equality node here for these 2 likelihood nodes. Essentially, in this larger data set, if we were to do 536 observations, we can create a model that has 536 repetitions of this basic same factor graph structure, and that's what you see here. That's this massive jumble of the factor graph. So these factor graphs, they do become quite large for IID models, but it's good to keep in mind that this is just the n times repetition of this same basic factor graph structure. And that's also how it's implemented under the hood. But if you visualize it, you'll get something like this. Right, so we'll define a message passing algorithm in the same way as before with the Probabilistic Programming 2 session. We'll feed in data, the entire data set. We'll perform an update step. So, and because this is an exact Bayesian inference setting instead of an approximate Bayesian inference setting, with a single update step, we have computed the posterior for the weights. And if I visualize the prior distribution over these parameters, theta 1, theta 2, it'll be a nice widely spread out Gaussian distribution. And then after n observations, the thing has really shrunk to a very narrow region of parameter space. You can see that this is these x1, xy axis. This is parameter space. And the axes are exactly the same. You can see where this left-hand thing is quite spread out, and this right-hand thing is quite concentrated on it. That's why we refer to this. It's quite concentrated on a particular region of parameter space. You can also see that here that the top, the height of this probability distribution is about 0.15. That's the probability density at the peak here. And here you can see it's much, much larger. So it's really gone from a flat distribution to a very peaked distribution in a short, in a small confined area. And that signifies that with high certainty, we know that these distributions are located around that peak. We can see the slope coefficient is nearly 0, and then the intercept coefficient is slightly above 0. And if we visualize that, it's a slightly decaying line from September 2010 to February 2011. So there's it's not a good time to make money on the Turkish stock market. And so if you're interested in financial trading, you'll have noticed a couple of things. Most people, when they talk about high frequency trading, they'll talk about predicting these very small variations. And that depends on a lot of different factors that we haven't taken into account here. And if you're thinking of low frequency trading, so just investing in something and then waiting for a while, and as the company that stock belongs to, as that grows over time, they'll become more valuable. And you would expect that in 5 years' time, if you look back at your stock, that it will have become more valuable. So then in low frequency trading, you would expect to see a small positive trend over quite a long period of time. Then there is still this particular, it's a note here, but it's something that will come back when we look at dynamic models. What I've done here is I've coded up a model where we have n instances of an input variable and n instances of an output variable. And that creates this massive factor graph. With Bayesian inference, you can also perform something called recursive estimation. So you can essentially start with a prior, make a single observation, compute a posterior, and then treat that posterior as the prior for your next observation. So basically move recursively through your data. And that means that this single factor graph structure that's repeated a lot of times in the IID model, this is sufficient. So we can just use this and change the prior parameters. So we can update the prior parameters, which is what we do here. No, that's not what we do here. Mu theta and sigma theta, that's the prior parameters. And if we plug in the mean of the previous posterior and the covariance of the previous posterior, then we're basically updating these prior parameters, and we're recursively moving through the data set. That's a lot faster. So, hold on. Oh, I forgot to time this. This roughly takes 10 or 20 seconds, I think, to compute for this large IID model. And then here it takes less than a second to go through all of the data points. And again, if you visualize it, you'll end up with a very similar posterior. It's not the same posterior, but it's a very similar one. So this is mostly due to how we're doing this probabilistic programming. So the math is the same, but the execution in terms of the algorithm that we're running to compute the posterior, there's a slight difference in doing a batch estimate, as it's called, with n ID samples at the same time, or recursive estimation, where we update the posterior recursively over time. Those are two different forms of inference executed, two different forms of execution of inference that becomes an option when we're doing probabilistic programming. Any questions so far?
Yeah, I have one question.
Yep.
Can we go to a part of the state functions with non-recursive model?
This one.
The step function. I think it's the next
function.
cell. Yeah.
Yeah. Yeah.
So we only update once over here. We didn't update it after every observations, or.
So here all of the observations are fed into the model at the same time. So this particular structure is called a for loop, but it's basically we're taking this vector dates num, and we are augmenting it with a 1, and that's a mathematical detail that's talked about here. If we're taking a linear function between theta1 and theta2 and x, then this will be theta1 times x, theta2 times 1, and theta2 will be the intercept, and theta1 will be the slope. But that's, yeah, so that's just a mathematical detail, but it's still something that needs to actually be done in code. And this is where we do that. So we take this the ith component of the x variable, and then we put that into a column vector with a 1 at the end. And we do that for all I is 1 to n, for all samples. And we place that into a single list. So this particular object that I've highlighted here, that's the entire data set. That becomes part of this data dictionary, and this data dictionary is here.
Yeah, but I still a little bit confused about what exactly is the difference between non-recursive model and the recursive model. Like I think the step functions works in the recursive model would be like it's like changing the posterior into the prior after every observations. And in this model, in this non-recursive models, what exactly it works inside?
I can show you that. Give me a second. So what you're going to see for a moment is that the ID model with the batch estimates has this really large factor graph, and this factor graph links all of these observations together, and they all point towards a common set of parameters theta. And if we want to do message passing over this large factor graph, there's an underlying compiler, a scheduler, that figures out which messages have to be sent where. If you look at the step function that's derived by the compiler, you can see that it is huge. It contains well over 300 messages, and basically absorbs all of the data at once, computes all of these messages, and then all of them combine into just like we had here, combine into an equality node going upwards to an unknown variable theta, and that's combined with the prior. If we look at the recursive model, let me just go down. you can see that this step function is much simpler. It just has 3 messages. It's basically just this factor graph. So it'll take the observation from Y, the response. This likelihood variance is also clamped, so it will compute this message going this direction. And it takes this this knowledge of X, the input variable, and then it computes a message towards theta, and the message from the prior towards theta, and then it updates the posterior for theta. So here there's just, these are just the computations for a single observation.
Mm-hmm.
And then what we do here in this, so how is that then different? During inference, we loop over these samples. So we start running for I is 1 to n, and then we just feed in the current input variable augmented with this this one parameter, and then the current response, and then we use the mean and covariance of the previous posterior as the prior parameters. And then we'll do a single step to compute the posterior at time I. Then we move forward with this for loop, and then that posterior that we just computed becomes the prior. We plug it in as prior parameters.
But
Look
in
at
this
the new
case,
observations.
like in this
Yeah.
case, we have to do it like 51 times, right? So why?
Yeah,
So why
530 times.
it has the less computations?
So it's just we are doing well, that's a good question actually.
In the non-recursive models, we only do it once, but in the recursive model, we just repeat it a lot of times. So I can understand why there's have the different computation.
Yeah, so actually what's happening in the batch estimate is that so in the recursive estimate, the posterior at no, that's not getting to it. I think this is I think a good question.
And I also don't understand why it caused the different results, because in my opinion, is that non-recursive model just put it all in once, and the recursive model just do it, repeat it one a lot of times, but actually their sub factor graph is the same, right? If
It
we
is
just
the
look
same,
at
yeah.
one cell, yeah.
Yeah.
And the message passing is always past the weight, so I don't know where's the difference between these two models.
I think this is a good question. I will think about this for a bit.
But if we see the results, the non-recursive model and the recursive model would have the difference posterior in the end, right?
Yeah, so this one indeed is different from the, so this one peaks at a probability of 300, and then this one peaks at a probability of 200 sort of. And we know that there's, yeah, so so we know that if you're doing batch estimation and recursive estimation, after observing all of the data samples, you should get the same posterior, but we are not getting that here. And but that's mathematically, we should get the same posterior. And I think that's not the case here because of how Formulab implements this message passing procedure, this software package. And I'm not entirely sure where this difference then occurs. It could be either in how this equality node is implemented, and you know, if these messages all come in. This is a great question. I don't know.
Yeah, okay.
Yeah, so we know for a fact that So there's this great book. It's not entirely sure whether it's also in the reading list of the course. I don't think it is. It's called Bayesian Filtering and Smoothing by Simon Seca. Has a chapter, Batch versus Recursive Bayesian Estimation. Hold on.
Okay.
So the whole chapter is about batch versus recursive Bayesian estimation. It also starts with linear regression. And we have this really wonderful result that mathematically speaking, convergence of the recursive linear regression parameter means the final value is exactly the same as that obtained with batch linear regression. We do know that after observing all of the data points that mathematically, the posterior produced by a recursive procedure should be the same as the posterior produced by a batch procedure. Now that's not happening here because this distribution that I plotted here peaks at 300 and this distribution that I plotted here with recursive estimation is at 200. But I cannot really tell you concisely why that's the case.
Yeah, it's okay.
Now that I think about it, it should be the same, yeah.
Can you pass the information of the book on the maybe PSR or something?
Yep. I'll do it in the Teams chat.
Yeah, thanks.
Thanks for a good question. Shokai, right?
Yeah, thanks.
Yeah. It might just have something to do with the plotting functions. That's still a possibility.
Sorry, I have another questions about the assignments. If we do it in different models, the result would be fine if we use different non-recursive or recursive one, right?
Yeah, that's fine. So
Okay.
what I'm looking for in the assignment is just to see that you know what you're doing. So we have a model description here. Can you translate that into basically a factor graph description of a probabilistic model?
Mm-hmm.
And can you execute the right commands to automatically infer posteriors? And then later on, we'll involve both a bit of math and a bit of computation. But in general, we're just looking for, do you know what you're doing? Yeah, I don't have a very specific, I don't have a single answer in mind.
Okay, thanks.
It seems to be the same. Yeah, it is the same posterior. It's just plotted differently. Okay, I think that resolves it. It's the plotting function. Right. Okay, I found it, Shakai. It's a very easy solution. Here I'm using the ranges -0.5 to 1.5, and here -2.5 to 2.5. And that yeah, so I get this x-axis -½ to 1.5. And then here I'm using -2 to 2 and -3 to 3. So if I change this, then I'm guessing, yep. Yeah, so they are exactly the same. My apologies for the confusion.
But I do it in the non-recursive model ways, and my friend do it in the recursive model ways, and we got 2 different results, but it's pretty similar, what I can say, but it's different.
Well, I would have to look at your code, and perhaps there's an approximation step somewhere in between that is being handled differently.
So if we have any questions about the assignments, can we ask you directly, or?
Well, you can post it on Piazza, because then if I answer your question, then other people or other people with the same question might not benefit from the answer.
Okay, thanks.
Okay. Any more questions at this time? Okay, then I'm going to move on to the credit assignment problem. So we'll be doing, this is a discriminative classification problem. Sorry. Now we're talking about a bank which has kept track of individuals that they have granted credit. So either in the form of a mortgage or a small loan to start a business, or expand a business or something. I have forgotten what these features were, to be honest. But suffice it to say, they are 2 features that describe the applicant in some way that the bank deems relevant. And then each of these individuals has been labeled as, we have given this person a grant, and given this person a loan, or we have not given this person a loan. And so that's described as successful or unsuccessful. And perhaps it's even better just to consider this as 2 features, feature 1 and feature 2. And as you might already see here, these 2 clouds of red dots versus blue dots, they are not clustered. They are actually quite mixed. And so this is not going to be an easy classification problem. Still, we're going to give it a try. And here we have just the model description. Again, we'll be working with the same situation of a likelihood of an output variable given input variable and some unknown set of parameters, theta, and a prior distribution for those unknown parameters. We would like to obtain a posterior for theta given the input and output variables. And in this case, we will not have a Gaussian likelihood because a Gaussian is a distribution over the real line, so you can get some continuous response, a continuous output. And in classification problem, we have discrete output, in this case, binary. But if you've read Bishop, then you've seen that we can formulate a likelihood function with a logit distribution, which is short for a Bernoulli distribution with a sigmoid transfer function. So why this structure? We have some variable x, which is the output of this linear function of the input variable. Then you push it through this negative exponential, which is like a decaying curve, and then you take 1 over 1 plus this decaying curve. You get this sigmoid structure, sigmoid after an S. So it looks like a forward S. And this effectively maps the output of that linear function of the input x, effectively maps it from the real line into the 0-1 interval. And then once it's in the 0-1 interval, it can act as a parameter for the Bernoulli distribution. And the Bernoulli distribution governs, is it going to be 1 or 0? It's a distribution for binary output. And so now we with this logit likelihood function, by plugging this in instead of the Gaussian likelihood function in the previous model, we now have a Bayesian classification model. Again, we can use the same prior distribution, And Formulab has this convenient logit node, this logit likelihood function. That's just part of the zoo of nodes that's available in this vector graph toolbox. Still, as you may have read also from Bishop as a background, this logit function requires an approximation. So there's a local variational approximation parameter, xi. And so we'll be specifying this as well, this psi here. That's part of this input node. I am not going to ask you to repeat the derivation for this local variational parameter, but it is an interesting thing, and reading this part of Bishop for this Bayesian logistic classifier is, I think, great for your understanding of variational inference, variational Bayes. And I highly encourage you to go and read that section of Bishop, figure out what this local variational parameter is and how it's being used effectively in this particular model to do Bayesian classification. Given that we now have two unknown parameters, so not just these parameter theta for the model, we also have these local variational parameters psi. So now we're in variational Bayes territory. We have theta and psi, and we are going to specify that the model, that these are two different parameters, and we need two different posteriors for them. We need a posterior for theta, and we need a posterior for psi. But still, we can just call for a message passing algorithm to be made, and we do have to initialize some of these posteriors as we're doing here. So we're just creating a posteriors dictionary where we're filling in the keys for each of the psi variables from I to n with this particular setup. But that's you don't have to memorize this. But the same structure now applies. We are filling this the same structure as the batch model before. So we're filling this particular list with these features augmented with a 1, because that's still important. We're feeding that in as the input variables, the input data set, and these labels are the output variable. That's the data dictionary. And now we're doing variational Bayes, so we're iterating over these two posteriors. First, we'll update the posterior for theta for the parameters, using this entire data set and the previous definitions of the posteriors. And once we've found the set of posteriors for theta, then we can compute the posteriors for psi given the previous posterior for theta. And we'll iterate this a couple of times. So next time we'll be doing we're updating the posteriors for theta given the current posteriors for psi, and then we're updating the current posteriors for psi given the current posteriors for theta. We'll do this a couple of times until convergence. And if you paid attention to variational Bayes lectures, this will converge. And so if we take a test data set and parse that, we can compute the posterior predictive for the test samples, compute the labels using this function, which is essentially pushing it through a sigmoid and then rounding it, as in the decision threshold is the posterior probability belonging to class 1 larger than 0.5. Then it should be assigned class 1, if not assigned class 0. We can compute an accuracy result here with, in this case, of 63%. And if you're a bank, I don't think you should be happy with a test accuracy of 63%. So the credit assignment problem is notoriously difficult. And even though you can, if you look at this data set, you can think of, well, maybe if I use a more complex machine learning model, perhaps something that's quite flexible, I can identify this region where there's apparently only red dots. You should know that there's so much individual variability between applicants that a lot of these models don't reach very high accuracy levels. Even with some huge model, some highly complex model, you will not get a test accuracy of 100% or 99%. Any questions on this part of the probabilistic programming lecture? All right, then I assume that all of this was clear and that you had no trouble getting through it. Then I will now switch to talking about the assignment. So I posted the assignment before the break for anyone that wants to work on the assignment before the break or during the break that they could. I have not been keeping track of Piazza, so if there are some issues with the assignment, I will have a look this afternoon and answer any questions on Piazza and perhaps even update the assignment if that's necessary. But I'll just introduce it now as if we're introducing it, as if this is the first time that you see it. So in this assignment, you will be using basically everything you've learned in the probabilistic programming session so far. It consists of 5 questions, and the first 3 questions are, you can do that basically if you've worked through Probabilistic Programming 3 and if everything's clear to you and you feel comfortable with applying Formulab and a factor graph description of probabilistic models, then you can, so those Probabilistic Programming 3 should help you just in answering the first 3 questions. For the final question, the final 2 questions, you're going to need Probabilistic Programming 4. Why? Because Probabilistic Programming 4 will go into variational Bayes a bit more, and also this free energy objective function that you need for the assignment. You can, so that's all detailed in Probabilistic Programming 4. The problem itself, it's about an airfoil, so a wing. And NASA has put a lot of these wings in wind tunnels, and I mean, you've seen this before on YouTube. I think they'll put some object in a wind tunnel. You can put a point of smoke at the start of the tunnel, and the smoke will pass over this object, and they'll visualize some of the effects of aerodynamics of the object. So in this case, as the wind is traveling past this airfoil, it's going to produce these vortices or eddies in the air current, and these have various effects on the wing. So some will create additional lift, some will make the wing vibrate a bit. And as you've been on a plane before, there's always a lot of background noise. Part of that noise is generated by the wing itself, because the wing, one of the effects of the wind current after the wing is that the wing will start to resonate. It'll start to vibrate at a particular frequency depending on the wind speed and everything. And metal objects that vibrate at a certain frequencies will create sound. So these wings traveling at certain, if you're traveling at certain speed, at certain altitudes, these wings will start to make noise. And NASA has measured that, so we'll have an input variable here with the frequency of oscillation of the airfoil itself, and then they've measured the sound magnitude level in decibels. And you can see this is really a beautiful relationship. What you see here is the multiple measurements for additional factors that are not included here. So each of the dots, you can see there's 4 dots here. And each of these dots is a different value for a different variable in this experiment. But I've neglected all of these, and you can just think of them as repeated measurements of this particular frequency level. And so we're going to fit a regression function through this so that NASA can interpolate. So if the wing is vibrating at a frequency in between these 2 frequencies, then I expect it to produce sound of a particular level, which is predicted by the regression model. And so in Bert's lectures, he talked about linear regression, and then about these basis function expansions, specifically this Gaussian function. Another popular class of basis expansions is polynomials. That's something you've probably seen before. I cannot imagine that you are unfamiliar with what a polynomial is. In this case, we'll be using a polynomial base expansion. So we'll just take some input variable x. We'll have x to the power 0, x to the power 1, x to the power 2, x to the power 3. Going forwards up until x to the power d, so up to an order d. And our model will be the inner product of some parameter theta and then the base expansion of the input variable. So here we just have a single input variable frequency, these levels, and we'll basically expand that to a vector of size d plus 1. And now we have d plus 1 parameters for this expanded vector, this expanded feature vector. But other than that, the model is still the same. So we have this function, this polynomial function, and we have some noise, which is zero mean Gaussian distributed with some precision tau. Yeah, this is some. You can do this polynomial expansion in advance. You can create something called a van der Monde matrix, and that's easy to work with if you're doing visualizations later on. So keep this in mind. But essentially, your first question is to specify a polynomial regression model of order d is 3 using Formulab, and then define a message passing algorithm and infer a posterior. So that's very much similar to this first session of Probabilistic Programming 3, this first half. And so if you've paid attention, the one component that is not described in this polynomial regression part is in this problem of economic growth, we have fixed this noise variance, sigma squared y. But in the assignment, I've not fixed tau. I'm not giving you a value for tau. So in this first question, what you just have to do is calculate the variance of the observed signal per distinct frequency level. So basically, look at a particular frequency level. You can think of these as repeated measurements, as I mentioned. Compute the variance within each level. Do that. What's the variance here? 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 Etc. Just average that and then invert that and compute the variances, invert these values, and then average over them. And that'll be your guesstimate of tau, essentially, of this likelihood precision. And if you think, well, what a cumbersome and weird way to populate this parameter, populate this value, you're right. And this is a very unprincipled way to tackle this situation. And in the next question, you are going to simultaneously estimate tau and theta. Both of them are unknown parameters. We're Bayesians. We just put priors on them. It passes through a likelihood function, and we obtain posteriors for them. That's how you should tackle this problem. But for now, just to sort of space this assignment a bit, you're just going to compute the variance and then run the simple polynomial regression model. And once you have computed the posterior, you can extract the maximum posteriori estimate from the posterior using this Formulab.unsafe_mode function. And I've added, so this unsafe part is an internal method to deal with numerical stability. So just ignore that for now. You can just think of it, I want the mode of this posterior. And then once you have that, that's this theta map variable. You don't have to do anything about this cell. You can just run it, and it'll show you the polynomial regression model that you have inferred. It just shows you a single line. That's the map estimate of that polynomial regression that you've inferred. And you should then that cell is going to overlay that single line, single plot over the training data. And that's just a small sanity check to see whether you've gotten something reasonable, whether you've not, if nothing's gone wrong, then you should have gotten something that looks fairly reasonable. The second question is that you are given test data as well, and you are going to compute the posterior predictive distribution for each test data point. So Bert has a series of equations in his lecture for how to compute the posterior predictive distribution for a linear regression model. And note that, so this is polynomial regression, but the model is actually still linear in the theta component. So you can actually just follow Bert's derivations, and that should give you a posterior predictive distribution. Then there are some instructions for how you're going to visualize that posterior predictive distribution. So you're going to first scatter test data points, and then you're going to add the means of that posterior predictive distribution as a solid line, and you're going to add a ribbon as a prediction uncertainty of sigma. So that's going to that is your posterior distribution at every time step, and you're going to properly visualize that for the test data. In question 3, I'd like you to compute the maximum likelihood estimate on the training data set, and then scatter the test data points, add the predictions of the maximum likelihood estimate. So again, that'll just be a single solid line for the ML estimate. And I'd like you then to compare the mean squared errors, or compute the mean squared errors for the ML point estimate and the map point estimate on the test data, and just compare them. And basically what you're seeing here is the difference between a uniform prior and a slightly informative prior, so a Gaussian prior. Both results are point estimates, of course, but this is going to be the effect of including a slightly informative prior on the data, or on the model. Question 4, we will now treat the position of the likelihood function as an unknown variable, so tau. You're going to have to re-specify the model, but now you're also going to assign a prior distribution to tau, and you're also going to re-specify the message passing procedure such that you simultaneously obtain posteriors for theta and tau. And so you've already done this, namely in the second part of the probabilistic programming session, where you simultaneously estimate chi and theta. So this shouldn't be too hard. And if you get lost, I highly recommend going through Bert's theory notes for the variational Bayes lecture. Then the final question, I'd like you to again compute a posterior predictive distribution. You can do this for a, so normally they require marginalizing over this precision posterior for tau, but you can use a simple approximation. You can take the map estimate of the posterior for tau, that's a point estimate, and then fix tau to that particular level, and then compute the posterior predictive distribution in the same way that you did in question 2. So that again give you a ribbon for the predictions, and if you're interested, which I again highly recommend to do, you can compare the two posterior distributions that you obtained from question 5 and question 2. So with question 2, it's with this guesstimated tau, which is, we know already that this guesstimate is off because here the variance is quite low and here the variance is quite large. So this guesstimate will be off. And in question 5, we're working with a principled approach for estimating an unknown variable, namely variational Bayes. And you can see that that posterior is going to be different from the one in question 2. And you can compare the two. That makes for a nice visualization. And in question 6, I specified before there were 5 questions, so there are actually 6 questions. The first 3 are you can do that with your knowledge of probabilistic programming 3, and then these final 3 questions you'll need the variational Bayes lecture for that. So in question 6, we're going to alter the inference procedure such that you also compute free energy as the objective function in this variational Bayes procedure. You're going to define models of order d is 1 to 5. So a polynomial model of order d is 1, of order d is 2, of order d is 3, d is 4, and d is 5. You're going to compute free energy for all of those models given your data. And then you're going to select one of the models, namely the one with the least free energy, the smallest free energy. And to answer this question, you just have to report the order of the polynomial. I still need to see you implementing that procedure, but you don't have to visualize the posterior predictive of the model with the optimal order, for instance. It's just fine to compute all of those free energies and then report the smallest, or report the order polynomial for which free energy is smallest. So that is it. Any questions? Oh, there are lots of questions. Harm.
Yes, I have a question about the unsafe mode.
Yep.
Why do you specifically use the mode instead of the mean or the median?
Well, we're looking at the maxima posteriori estimate of the posterior distribution. So the point for which the posterior probability is largest. And so if you have a distribution, the mode is the point for which it is largest. If I look at the normal distribution, so the mode is the peak, the point where the function peaks, where it's largest. And so if this is a posterior distribution, we want the point, the parameter that has the highest posterior probability. So we are specifically looking for the mode. And in a normal distribution, the mean and the median is for discrete distributions, but the mean and the mode overlap. So there's no difference there. But if I, for instance, look at a different distribution, the gamma distribution, in this blue line, this blue distribution, the mode is here, that's the peak. But because this distribution is skewed, it has more mass to the right of its mode than to the left of its mode. The mean is actually going to be here. It's going to be slightly right of the mode. And so if I select the mean for this gamma distribution, I am not picking the point with the largest posterior probability, which is what I wanted.
Okay, clear.
Yeah, okay. Shokai?
Yeah. Can you hear me?
Yep.
Yeah, I have a question too.
Yep.
Yeah, do we have to do the prediction? Do we have to draw the predictive line of the higher frequency? Like the higher frequency higher than the most highest data point inside.
No, you don't have to do forecasting.
Uh-huh. Okay.
So you don't have to consider this a signal. So if you have any signal, but perhaps a good example of that is if you have weather, or well, actually, this is also a good example. The stock market data. Yeah, so this is these are samples over time, i.e. a time series. You can do interpolation, so I can fit a model and then basically ask the model, so what is the most likely value of this the data generating distribution, the problem in between these two observations, interpolation. And I can do also extrapolation, say, okay, what if I were to, I want to predict how this process behaves in the future. For instance, if you're doing stock market predictions or weather predictions, then you would like to basically extend this model in this direction and make predictions there. You don't have to do that here.
If I already do it, can I just keep it like that? Or I just
Yes,
delete it?
but I mean, you have to do, yeah, I mean, that's fine, but also make sure to do interpolation. So make sure to compute the posterior predictive on the given test data points. You can,
Yeah.
essentially what
Yeah.
you're doing is you're creating new test data points. So what if I so what if I in the future would like to measure this at a different frequency level, higher frequency level? Yeah, so that's fine. You can visualize it for new test data points, but make sure to visualize it on the existing test data points as well.
Yeah.
Because that's something that we use to validate, to verify whether your model is doing what it's supposed to be doing.
Yeah, clear.
Okay. Still, I mean, kudos for forecasting. Ron.
Hello, can you hear me?
Yep.
I have a question regarding error message.
Yep.
May I share the screen, or can I just send a screenshot in the chat, or? Because I think it would be better, or I can just describe it because it's not that difficult. What would you prefer?
Okay, yeah, you're. It's okay to share your screen, but make sure to.
Yeah, I will hide the important code. I will not show all my code.
Well,
Yeah.
also any personal information, because we are recording
I'm
this
sure-
live class
Yeah,
recording,
I'm sure.
and it's
I'm pretty
going on
sure about
YouTube
that.
and
So
everything.
yeah.
Okay, then go ahead. I'm not sure if you can share your screen.
Let me check. Yeah. Can you see it?
It's coming up. Yeah. Yeah.
Can you see it? So
Yeah.
this is the error message. It said that the distribution is improper, and actually there's a, and as you can see here, the training result is probably untrained, because actually after, for example, like 3 loops, the distribution becomes improper and it cannot follows the library. But the problem I figure out is that actually when you change the precision or variance, wherever, like, actually can run. Now you can see it. You can run that.
I can explain this very briefly, what's happening here. So Formulab is doing inference. So all of these mathematical equations that you've derived or that you've seen BERT derive, there's some matrix or some matrix vector product, there's a matrix inverse, there's all these algebraic steps that have to be taken. And mathematically, we know that certain properties hold for certain matrices. The covariance matrix is positive definite. We know that is just a property of that matrix. But if you implement this in a computer, then you're going to run into numerical precision problems. And so one of the things under the hood that Formulab does is it maintains not just a mean precision parameterization, but something called it's the information parameterization of the Gaussian. So it has as one of the parameters, it has the precision times the mean, and the other one is then the precision. And this chi thing, you can see that mean, and then the Gaussian symbol, and then xi is, etc. That xi, that is the precision weighted mean. And I'll show you that in Wikipedia what it looks like in a minute. But Gaussian Formulab works with these alternative parameterization of Gaussians, weighted mean precision and precision. And it does that to avoid certain matrix inversions. Still, in this particular problem, it will have to invert a matrix sometimes, and so sometimes it has these elements in the matrix, and it's going to round off certain values on the off diagonals or on the diagonals itself. It's going to round off certain elements in that matrix, and then when it tries to invert it, it's just barely singular, that matrix. Mathematically, it is not singular, but purely the implementation of this matrix inverse operation under the hood, through these rounding errors, a singular matrix arises, and then when it tries to invert the singular matrix, it fails. And this particular error message, the mean is undefined because the distribution is improper, points to the fact that this W, the precision matrix that's shown here, in its rounded off form is singular. And one way to get around this is to replace this mean and conv that you have above your cursor there. If you replace mean with unsafe capital M mean, and if you replace conv with unsafe capital C conv, the error message should disappear.
Unsafe, like
and then the capital M.
Unsafe capital M.
Yeah.
Unsafe mod.
No, mean, unsafe mean. And then just delete the mean afterwards, yeah. And below that, use unsafe conv, and you might have to write Formulab in front. So Formulab dot unsafe mean and Formulab dot unsafe conv.
I'm not sure if I pronounce it. How do you spell it?
F-O-R. Yeah, it's written there, yeah. And then dot unsafe mean, and then below that Formulab dot unsafe conv. And
let's see.
You're right that this gamma.
It's working. Okay.
Yeah. You're right that this gamma y fixes it because the this gamma y is it scales the covariance matrix. So if you scale the diagonal elements higher, then it's going to make it's probably going to avoid all of those rounding.
I understand it's some like computer issues, because if you are using the regression formula, like using alpha over beta times the identity matrix and plus the x transpose x, then inverse it like the normal regression, but the Bayesian version, you can actually get the correct result. But if you are like using the Phonolab here, you cannot get the result because some computer issues, and there's no way we can fix it because we didn't write the library, right? So yeah, so this is my problem.
But this is exactly the kind of question that you should ask in Piazza, because it has a simple fix, and then everyone can see the answer.
Which I did.
Yeah, okay, sorry, I haven't seen I haven't seen Piazza over Christmas.
Yeah, and also another question is that I wonder if the test set and the training set is actually inversed, because we have like 51 training samples and 500 testing samples, and when we are plotting our uncertainty bars, the uncertainty doesn't match the real uncertainty because the data samples are not given in the correct. Let me probably show my plot. It's like here. So as you can see, the uncertainty bars doesn't really quite fit the real, like the scattering of the points, right?
So the two data sets are not reversed. Okay, you are given so basically in any classification regression setting, you are often given a limited training data set, and then when you deploy the model in a pipeline or in a machine somewhere, it's going to run into much more test samples than you have training samples, and those test samples will vary more than the training samples. So this is sort of a realistic depiction of a problem. You're given a limited training data set, and then you have to generalize to a larger test set and your training data set, because of the fact that it doesn't contain an infinite number of samples, might not be fully representative of what you get in the test data set. Yeah, and what you need then is a model that, but what you then need is a model that takes that knowledge into account. So most of these maximum likelihood estimators, point estimators, they tend to overfit. That means that they tend to fit the training data very well, and they won't fit the test data very well, because they fitted the training data very well. But the training data is not always a perfect representation of what the test data set might look like. What you need is a model that sort of fine-tunes complexity such that you get a good fit on your training data and also a good fit on your test data set. And so this is also what was supposed to happen. I think maybe if you change the prior parameters, the curve will change a bit, and maybe if you increase the order, it will curve more. And if I am not mistaken, the ribbon on your posterior predictive should be larger. At least my answer model has a larger ribbon. I think there might still be something for you to look at there. But the data sets are not reversed. This is an accurate reflection of what you might come up against if you're building machine learning models for a company or in real life.
Okay, thank you.
Yep. Harm?
I already asked my question.
Oh, okay, sorry. Oh, yeah, you still had your hand up. I thought you had a new question. Okay. Are there any more questions on Probabilistic Programming 3 or on the assignment? If you haven't started yet and you are starting on the assignment now and you're running into some problems, then just post them on Piazza. I'm back from break, so I will regularly check Piazza and answer your questions there. I think the assignment, it looks quite extensive, 6 questions. Each of those questions has 4 concrete steps, which all contain several lines of code. It might look quite extensive, but the assignment is a combination of the third and fourth probabilistic programming session. We are not really doing anything new mathematically. Polynomial regression is new, but you've seen basis expansions under the Gaussian expansion in Bert's lecture before. So I personally just don't consider that something new mathematically. And I think it tests your, I think it's a fairly real world problem. It's something that has actually been done and was published as which means that people thought it was a valuable piece of insight. I think it's also, if you master this, if you can do this assignment on your own and you understand all the math and you understand what's necessary to infer these posteriors, then you have a very valuable skill set that you can apply over and over again in your future career. Because yeah, it's a polynomial regression model with Bayesian priors where you simultaneously estimate different parameters. It's quite an advanced and useful skill. Any other feedback? Yeah, you can also just post it on Piazza. I'm going to wrap up the lecture now, so we'll stop recording in a bit. So if I can just go back to just share. Just to reiterate, to be clear about this, today we've done Probabilistic Programming 3. It's a catch-up lecture session. On Wednesday, we will have Bert's lecture on dynamic models. On Friday, we'll have Bert's lecture on intelligent agents and active inference. And then next week, Wednesday, we'll have Probabilistic Programming 4, latent variable and dynamic models. I can answer questions on the assignment as well next week, and maybe some questions popped up since then. Afterwards, so next week Friday is the bonus lecture by Magnus on what is life. It is usually regarded as one of the most interesting lectures in this course. It's also Magnus is a gifted speaker, so that's usually something that students enjoy. And then the 3rd of February is the written examination. I think I've set the assignment to, it's due the 24th of January. Yeah, so that's the Monday afterwards. So that's in 2 weeks' time. So you have 2 weeks for the assignment. Well, more if you have worked on it in the Christmas break already. If there are no further questions, I am now going to stop recording.